Let's conclude with a couple of example problems. The first one will be quite easy, relatively, and the second one will be a little more challenging. So we have a roller coaster, no friction, that's nice, and we need to determine various positions here, A, B, and C, what minimum height is needed so the car does not fall off the track at position B. So we need to consider how fast it needs to go at this point so it doesn't fall off. And that speed is going to require a centripetal force acting down. That's everything that gravity can give it. And no less, because if it's less than that, then gravity is still going to give all it has, and it'll pull this cart off the track, and you won't remain in contact, and that will probably hurt quite a bit. So the minimum speed at V is given by gravity, mg equals mv squared over r, the centripetal force. So V is rad rg. So then from A, we have that work done by gravity, which is the only force doing work here, is delta K. And we'll recognize that in delta K, the kinetic energy is the speed required at B that we just got. So expanding this energy condition at position 1, which will be A, K1 plus UG1 is K2 plus UG2, position 2 being at B. So it's not moving at A, so we can cross kinetic 1 out, and then solve for mgh at position 1. H is what we're looking for, equals 1/2 mv squared. And we already solved for V, so we can plug that in for V squared, plus mg. At position 2, our height is 2r off the ground, which is our reference point. So the m's go away, and we have h is divide everything through by g, and we have the answer. Namely, h is 2.5 r. So actually, height has to be greater than equal than 2.5 times the radius. Let's do the problem again, this time starting at a height of 3.5 radii. And we'll compute the speed, radial acceleration, and tangential accelerations when the car zooms down this ramp, woo, goes over point B with more than enough speed now, right? Because we're starting at a higher height, and those conditions spelled out at point C. So from A, work done by gravity is delta K, because that's the only thing doing work as it goes through this loop. And you probably should realize that it doesn't really matter that it goes through the loop, because the forces acting on the cart are perpendicular wherever it is. And even though there is gravity, which isn't always perpendicular, it's conservative, so it doesn't matter if we consider from A to C being direct or going around the loop and considering it there, which it is in actuality, but it doesn't change the computation of the problem. So position 1 is A, position 2 is C. We have K1 plus UG1 equals K2 plus UG2. It's not moving at position 1. So the speed is going to be embedded in K2, which is UG1 minus UG2, which is mg h minus r. We're starting at h, and we're concluding at a height of radius. So 1/2 mv squared equals mg times 2.5r. The m's go away, and v is easily solved, rad 5gr. The tangential acceleration at C is strictly due to gravity, acting straight down, which is 9.8 meters per second squared. So the radial is the perpendicular, v squared over r. We've already solved for v, so 5gr over r, so we have 5 g's of acceleration at point C. So now we enter into our slightly more challenging and hopefully kind of a fun problem here. We have a skier at the top of a very large frictionless snowball, given a slight nudge and then skiing down, and at what angle does she lose contact with the snowball? So that should be fun. So we're starting at position 1, and you're going to move to position 2, and there's going to be some angle that is traversed that we're looking for. What angle does she leave the snowball? Now keep in mind, it's not going to be way here at 90 degrees, right? That's not going to be the case, because if she's moving along this snowball, then she's going to leave at some point. We're going to call that point position 2. Well, this isn't just a single-faceted problem. We're going to have a couple problems to solve here. We're going to consider energy first of all. But recognize, before we embark into this, that this may not be as fun as you think, because there really is no bottom to this situation. And therefore, this could be very hazardous to your health. Now, of course, it's really ridiculous for a physics teacher to say V terminal is infinity. That's obviously not possible, but you get the point. Anyway, so we start with the idea of energy. Work done by gravity is delta K. So from position 1 to position 2, what we're really going to get here is, in doing this energy equation, we're going to solve for the speed at position 2 in terms of angle theta. And then we're going to have another problem to solve to really figure out the problem fully. So K1 plus UG1 is K2 plus UG2. There is no K1. And we'll consider gravitational potential energy being 0 at position 2. So that really simplifies our equation down a lot. So we start at position 1, radius r, and at position 2, it's the same thing. So what we really need to do is figure out the reduction in height going from position 1 to position 2. So now you can see it. This is the trajectory that we travel along to position 2. So this is our delta y from position 1 to position 2. So K2 equals UG1. Let's expand that. 1/2 mv2 squared, which is the v2 is what we're looking for, is mg delta y. M's go away. And we have v squared equals 2g delta y. So that's 2g times, well, what is delta y? It's this quantity here. So it's radius r minus this part of radius r. So that'd be r minus this. But what is this? Well, this is just r times cosine of theta. So we have r minus r cosine of theta. And we have then our equation for speed at the point in question, which we don't know where it is yet, but that speed is going to be rad 2gr times 1 minus cosine of phi. All right, so now we know the speed of the skier at the moment she exits the snowball. But when does she exit the snowball? What condition must be met for her to exit the snowball? Well, if you think about this for a moment, you have to conclude that if she exits the snowball, she's no longer pressing on the snowball, nor is the snowball pressing on her. Therefore, that must mean that there can't be any more normal force. So when is the normal force equal to 0? Now that will be a lot of fun. Why? Because she will feel weightless, and that's worthy of a lot of cheer and happiness as you experience weightlessness. In any case, she'll exit when that normal force drops to 0. Now the normal force arises from the radial component of gravity. So here we have gravity acting down, and there's alternate interior angles, phi. So what part of the gravity is the pertinent part here? Well, it's this part. This is the radial part of gravity, giving rise to the normal force. So what provides F sub c, the centripetal force needed to traverse this circle, which she's on at the moment? Well, it's Fg radial. So Fg radial equals mg cosine of phi. Mg cosine of phi is the radial component. Now keep in mind that that radial component is maximum up here at position 1. And as you go around the snowball, mg cosine of theta is progressively approaching 0, and it'll be 0 here. So there will be no force of gravity trying to press the skier into the snowball. Therefore, the normal force goes from maximum to 0. Well, somewhere along the way, you're moving at a speed, And you need a certain centripetal force to move in that speed. Well, what is the centripetal force provided by? Well, of course, that is mg radial, is what provides that centripetal force. So when the radial component of gravity equals the centripetal force, the normal force will disappear. So keep in mind that the centripetal force is getting greater and greater as we traverse down the snowball. As the centripetal force goes from zero, no motion, to greater and greater, the mg cosine of theta, the radial component, is getting less and less at some point, namely this position. Those two forces converge upon each other. They become the same, and the normal force goes away. So it's orbiting at that moment. You're orbiting the snowball, and then a moment later, you're really exiting the snowball because your x component of velocity is not changing. So the sum of the forces is MAC. So we don't have to worry about the fact that mg acting straight down. There's going to be a tangential component, but we can ignore that because once you leave the snowball, at that moment, that precise moment, you have the sum of the forces being the centripetal force as you're orbiting. And so you have mg cosine of phi, the force that's enabling you to orbit at that moment. Don't worry about the fact that you're tangentially accelerating. And that's mv squared over r. So the m's go away. And now we have an expression for v squared, gr cosine of phi. But we already solved for v squared in the first part of this using energy. So that's 2gr times 1 minus cosine of phi. So those two are equal. The g's go away, the r's go away. And we now have this simple expression. Cosine of phi is 2 minus 2 cosine of phi. Bring the 2 cosine of phi from the right over to the left. 3 cosine of phi is 2. Phi is the inverse cosine of 2/3, which is the answer to the question, 48.2 degrees. Wasn't that a fun problem?